Hi, I would like to present the results of our paper Effects of Markers in Training Datasets on the Accuracy of 60-Pose Estimation. My name is Janis Rosskamp, and this work was done in collaboration with Rene and Gabriel Zachmann. Let's begin with why 60-pose estimation is important. You can see here a small selection of possible applications. On the left, we have a scene in augmented reality. Here it is important to know the pose of objects in order to place virtual objects at the right location. In the middle, we have an example in robotics. Here, the pose of the objects must be known in order for the robot to grasp these objects. And on the right, we have a scene where surgical navigation is used in order to support surgeons in their task. For all these tasks, training datasets have to be created specifically. This is a problem because labeling of pose data is time-consuming and prone to errors. Here are some examples of existing training datasets and their labeling methods. On the left, we have TLIS, where textureless objects were recorded using a turntable to accurately determine the 6D pose. In the middle, we have the YCB video dataset, which is a huge dataset of video sequences where signed distance fields and global refinement was used to determine the 6D pose. On the right, we have DoPose 6D, where manual labeling was used to not just annotate tabletop scenes, but also more complicated scenes where objects might be in a box, for instance. Our solution to replace manual labeling is the use of marker-based optical tracking to determine the 6D ground truth of objects. A possible setup can be seen on the right, where we place markers on the object and use cameras to track it. This makes labeling an automatic process with a high precision ground truth. But the problem is that neural networks might learn the markers on the object as specific features. During inference, we do not have markers on the objects, so the accuracy of pose estimation might be reduced. Keeping that in mind, we can formulate two research questions. First, is accuracy reduced if we have markers on object? Second, when we use high-precision marker-based ground truth, is it superior to imprecise manual labeled ground truth? Let's start with the first question, the impact of markers on pose estimation. To analyze the influence of markers, we create identical synthetic datasets where the only difference is the absence or existence of markers on the object. You can see it on the top row of the images, where on the left we have an object without any markers placed on it, and on the right we have the same object in the same scene but with markers placed on it. Additionally, we create a third and a fourth dataset to deal with feature learning of markers. In the third dataset, we use in-painting to remove markers from the images. You can see it on the bottom left. And in the fourth dataset, we randomly place markers on the object in order to reduce spatial learning of marker positions. We create datasets for two different objects. First, our T-box dataset. With the T-box you can see on the images above, where we have 20,000 images in 800 unique scenes. And then for the popular YCB video dataset, where we created 80,000 synthetic images for a subset of 5 objects. We train a state-of-the-art pose estimator, GDRNet, with its standard parameters. To allow for a fair comparison, we use the same seed for every experiment. To compare results, we use the ADD-S metric, which is the average distance between model points of the ground truth and predicted pose. We always evaluate on markerless test sets. Here are the results for our T-box dataset. Let's take a look at the ADDS metric. We can see that for a training dataset without markers, the ADDS metric is around 85%. For a T-box dataset with markers, this reduces by 8 percentage points to 76%. Using inpainting to remove the markers has the same accuracy than using markerless images. Marker augmentation or random replacing markers has a slightly lower accuracy than markerless images. So, to sum up, using inpainting to remove markers does not reduce accuracy compared to markerless images. So in the future, we will only compare markerless images with inpainted images. We also use the popular YCV video dataset for evaluation. Here we placed markers on the object and created a synthetic dataset. You can see the objects with their markers on the top row. We evaluated on both real and synthetic test sets. We only compared marker inpainting with markerless images because marker inpainting was the most promising method. Next to GDRNet, we also used the second state-of-the-art network called ZebraPose. Taking a look at the red numbers, you can see that the results between marker inpainting and markerless images is comparable. To make sure that our results are also valid in the real world, we created real training data. On the left, you can see markerless images, which we manually annotated. In the middle, you can see images with markers, which we automatically annotated, and then using inpainting removed the markers. Taking a look at the table, you can see that the results between markerless images and inpainted images is again comparable. Let's take a look at our second research question. What is the impact of inaccurate ground truth labels on pose estimation? We first begin by estimating the possible labeling errors. Here we manually labeled synthetic data with a known ground truth to estimate the labeling error. We didn't take into account any errors due to camera depth estimation errors. The distribution of errors can be seen in the table below. We then created synthetic data with inaccurate labels to use as training data for a pose estimator. Here you can see the results for a pose estimator trained on imperfect data. Without going into too much detail, high precision data is superior to imperfect manually labeled data. For more information, please take a look at our paper. To conclude this talk, we propose a novel method for automatically labeling training data for pose estimation. This automatic labeled data is superior to manual labeled data with imperfect ground truth. Our method is applicable also for moving objects and small objects where depth images might not be used for ground truth labeling. Some limitations are objects where we can't place markers or environments where motion capturing is impossible. In future work, we would like to collect training data with many images using our novel proposed method. Additionally, we would like to investigate if imprecise object marker registration reduces accuracy of our 60 pose ground truth and how this affects pose estimators. Thank you for your attention, and I would like to end this talk with a small remark. The code we used, so all the labeling tools, the inpainting, will be available on our website, which you can reach using the link or the QR code down below. Thanks and bye.